Welcome back to the second lecture, or should I say the continuation of the concept of black body radiation. So till this we have seen how different people or great minds came up with different expressions for the average energy density, and which fitted some portions of the absorption spectrum actually. Sorry, not to say absorption spectrum of the black body radiation, and we also saw that how their expressions fail at certain region of the spectrum, and we also saw that Planck have derived an expression, came up with an expression, which beautifully fits the absorption and beautifully fits the spectrum, and we are going to derive that. That expression is required for knowing how how this actually fits. We have seen actually it fits completely well. So I told you that during the derivation of the Rayleigh-Jeans law that the average energy term is the most important. That is what is changing in this. That is what is going to change in this derivation. So if you look, the average energy is given by kVt in the classical theory of electromagnetic radiation, but Planck derived it in a different manner. So certainly when the radiation is coming out of electrons, and there are large number of electrons, and their distribution is given by Boltzmann's distribution or Maxwell-Boltzmann distribution. So this is actually something very important. You need to remember this or know this, what it actually says. So it gives this is the number. This gives the number of oscillators having energy epsilon I at, this should be epsilon, let it be epsilon for the timing, and this is the temperature T. So we need basically we are focusing on the term of average energy. So average energy is given by total energy which is given by this expression summing over all the oscillators, energies of all the oscillators, and this is the total number of oscillators. This can be written as by N. So we need to find these two terms to get this, and we should start where we will need this expression actually to find both this and this term. So first knowing what this term what is the expression of this term actually. So total N is, this is the total number of oscillators, this is individual oscillator at energy epsilon I at time t, and summing over all the possible oscillators. So this looks like and so on. So using this expression we can get these terms, and this will be equal to So you need to keep in mind that I have used an expression for energy as, let's see, okay, this is the expression for the energy, which Planck took, that is, the energies are quantized, it cannot take any arbitrary possible value. This is the expression for this, and you can take n0 as common, which gives you plus so on. Now, to simplify this, you just need to take not take approximations at all, it's just simplification. So let x equal to exponential by qt. So b is a subscript here, so you should keep this in mind, and this expression simplifies to and so on. So by a little mathematics, you can know that this expression is given by or and so on. So the x square actually, and so on. So you get the total number of oscillators as this. The expression for the total number of oscillators is obtained, and if you do for the total energies of the oscillator, this is actually epsilon I. So epsilon 0 is 0 actually. So let me just erase it and rewrite it. So this is basically n0 0 n1 plus n2 and so on. Now you can again do the same substitution here, and this will be 0 plus n0 exponential of minus epsilon by kBt times epsilon plus n0 exponential of minus 2 epsilon by kBt 2 epsilon plus so on. Now, in order to simplify this, you need to take this, the same thing, then the overall expression becomes n0 is common. If you look at this, the epsilon terms, the epsilon terms are also common, and this is actually x. So you get x plus x square plus x cube and so on. Quickly doing this mathematics, it's not that tedious actually. So this is n0 epsilon x 1 plus x square plus so on. I did a mistake actually. Just check it. I forgot the terms actually. This is actually 2x square, 3x cube, and plus 3x cube and so on. So this will be 2x, taking x common, 3x square, so on. So this term in the brackets can be written as 1 plus 1 plus 2x plus 3x square plus so on is some derivative of this expression. If we look into this, and we have written that this expression is equal to, the expression in the brackets is equal to d by dx of, which is minus 1 by 1 minus x square times minus 1. Or this expression turns out to be, just keep with the flow of this language, this term becomes n0 epsilon x by 1 minus x square. So you get the term ni epsilon I summing over all i's, and you have the term for the total number of oscillators. So the average energy I am going to erase this side. The average energy then becomes n0 epsilon x 1 minus x square, and this is the this is the numerator. This is the numerator of E average by, if you remember this is actually n0 by 1 minus x. n0 by 1 minus x. Just let me check this once. Yeah, this is 10 by 1 minus x. So simplifying this, we get what is called epsilon x by 1 minus x, and substituting x, as we have taken x to be exponential terms minus epsilon by kVt, so and these terms become epsilon exponential minus epsilon by kVt by 1 minus exponential minus epsilon by kVt. Dividing the whole by exponential minus 1 by kVt, we get epsilon exponential epsilon by kVt minus 1. So this is the average energy. This is quite different from what we have taken in deriving Rayleigh-Jean's law, which took the classical term for the average energy equal to kVt. So I told you this is the important thing. So we have got the expression for the average energy, and now we need the average energy density in terms of so we need the average energy density. For this, we just take a derivative. So dE by d lambda is nothing but average energy times dN by d lambda. So if you look into the previous lecture, I might have written this as well in terms of I have written dN by d nu, which in terms of wavelength is given by this. So average energy has the form of this. So epsilon by exponential epsilon by this is actually epsilon by kVt minus 1 times times 4 pi L cube by lambda to the power 4. So this is the expression for the energy, radiative energy per unit wavelength, and if you want to know the average energy density, you just divide this expression by L cube and multiply by 2, because you need to take the polarization into account. So rho of lambda times T is 2 by L cube of this expression dE by d lambda. Okay, so what we get is something like 8 pi epsilon by lambda to the power 4 exponential epsilon by kBt minus 1. So this is the expression for radiative energy density per unit radiative energy density. So in terms of wavelength and temperature. So this is the expression. Now in the previous lecture I have written the expression that Planck used is something like rho lambda T is equal to A by lambda to the power 5 exponential epsilon by kBt. Sorry, it's B by lambda T. B by lambda T minus 1. So this was the expression, starting expression, which Planck used to explain the spectrum, and we can compare these two expressions because they are exactly the same. So what we get is comparing these two. I should write comparing. We get 8 pi epsilon by lambda to the power 4 is equal to this term, A by lambda to the power 5. 8 pi epsilon 8 pi epsilon by lambda to the power 4 is equal to A by lambda to the power 5, which gives A as 8 pi epsilon lambda. And this is something, an expression for A. Similarly, we can get an expression for B as well, because this is the expression for the energy density, average energy density in terms of lambda and T, and this is what generalized expression is. So if you look at B by lambda is epsilon by kV, B by lambda is epsilon by kV. Okay, so B is equal to epsilon lambda by kV, or lambda is equal to 8 kV by epsilon. Okay, so this is the term that we get, and you can substitute it here. Sorry, this is not 8 epsilon. There is some mistake. This is kV, B kV epsilon. Okay. You can write this equation as well in terms of frequency. So you have this expression, you can substitute it here, you will get some expression in terms of A and B. Just check it once. So if you are using this, from this you can get what is called 8 is equal to 8 pi BKB. Just check it, just substitute it here, you will get substitute this wavelength in this expression, you will get this. Also, we have got this expression. This is the main expression actually. So I am going to erase this everything and deal with so this is the expression for rho lambda times t, and we know that T is equal to we took epsilon is equal to h nu, which is just hc by lambda, and substitute epsilon into this. So this will come out to be rho lambda t is equal to 8 by hc by lambda to the power 5 1 by exponential hc by lambda kVt minus 1. So this is the expression, and if you again compare it with the generalized expression of rho lambda t as a by lambda to the power 5 exponential of b by lambda t minus 1, comparing these two, you will get a is equal to 8 pi hc, which is a constant, and b is equal to hc by kb. Okay, so you got the two constants as well. Now, I told you that the spectrum has two characteristics, and those characteristics are given by two laws, the Stephen Salesman Law and the Wien's displacement law. Let us just derive those two laws from this expression and obtain the two laws also. So I am going to erase all these. So the spectrum looks like this: rho lambda t lambda. So spectrum looks like this. Actually, it's not completely symmetric. It's quite towards this side. I should draw it in a perfect manner. It's like this. Okay, so I told you when I was talking about the Wien's displacement law that lambda max into temperature is constant, and lambda max is not the maximum wavelength. It is the maximum. It is the wavelength at which we get the maximum average density. So this is lambda max. So in order to obtain Wien's law, you can say that at this point the slope is 0. So if you just derive and take a derivative of rho in terms of wavelength, which is d by d rho, using the expression as obtained by Planck, 8 pi hc by lambda to the power 5 into 1 by exponential b by hc by lambda kb t minus 1. So this is the expression. We need to take a derivative of this. So if you take a derivative of this equation, this will come out to be 8 pi hc minus 5 lambda to the power minus 6 with exponential
hc by lambda kbt minus 1 as a constant
for this one.
Then this is equal to 1 by lambda to the power 5. Take the derivative of this will give you minus 1 by exponential. I'm not going to write the whole term, it's a bracket, minus 1 to the power square, exponential term itself. So just erase this. Exponential term hc by lambda kbt itself is coming, and then take the derivative of this also. So this is minus hc by lambda kbt square, lambda square t square. I guess this is the right expression for this, and the bracket is closed.
So nothing, it's like using the product rule. So it's lambda to the power 5 derivative of this, derivative of lambda to the power 5 minus 5. You get this, keeping this constant. You keep this constant, take a derivative of this expression, then take a derivative of this expression. That is the same thing, e to the power x, derivative of e to the power x is e to the power x, and then taking the derivative of this term. So it's like getting this expression as a whole, and then you can get 8 by hc exponential bracket minus 1 minus 5 by lambda to the power 6 minus exponential hc by lambda kbt by exponential bracket minus 1 times, this should be a plus, hc by there is a lambda hc by lambda to the power kbt, and there is a 1 by lambda to the power 5. So this terms and the derivative of this at this point should be equal to 0.
So putting this whole as 0.
So this term is not 0, definitely. So this is the term which is 0 in the case, and you can take hc by lambda max to be x. Then this is actually rewriting this actually lambda to the power 6 plus exponential hc by lambda kbt lambda to the power 7 hc by kbt lambda to the power 7 and exponential term as well. This term is the term which is equal to 0. So you can do this equation, simplify this, you can write this as hc by, I'm interchanging lambda by lambda max, which is the same thing because I'm going to get their Wien's law expression. This is this times e to the power hc by lambda max kbt by e to the power hc by lambda max kbt minus 1 minus 5 equal to 0. Just rewriting this equation to this. So take hc by lambda max kbt as x. This term becomes x e to the power x by e to the power x minus 1 minus 5 equal to 0. So
simplifying further, x minus 5 e to the power x, e to the power x plus 5 is equal to 0.
This equation can be solved numerically,
and what we obtain is something like this: lambda max into t is equal to hc by 4.96511 kb. This is actually a constant. You can check the values of h, you can check the values of c, you can check the values of kb, you can check the values of this constant. Anywhere, any book, you will get this value. Actually, this is the value of x. By solving this equation, this is actually x, and this is the Wien's law, or the Wien's displacement law to say it. Now we need to derive the other characteristic, which is the Stephen Salesman law. So, if you remember the expression for this, for the law, then it's actually E times sigma t to the power 4. Okay, so how to obtain this? This is actually the total energy, not the total energy density. So this is in terms of E lambda, this is written as E lambda, integration of rho d lambda, and this integration goes from 0 to infinity as wavelength goes from 0 to infinity. So substituting again for the value of rho lambda t, this is 0 to infinity 8 pi hc lambda to the power 5 exponential hc by lambda kbt minus 1 d lambda.
So taking out all constants,
get 8 pi hc 8 pi hc. Don't take out the constants actually, just substitute x equal to hc by lambda kbt. So lambda is equal to hc by x kbt. So d lambda will become minus hc by kbt x squared dx, and we need to substitute this into this expression. So this expression turns out to be 0 to infinity. It's actually infinity to 0 it will become, but it's the same thing actually. So 0 to infinity 8 pi hc by x kbt, just substituting lambda. This is and this is e to the power x minus 1 minus hc by kbt x squared dx. So simplifying it further, you will get an expression like this: 0 to infinity 8 pi kb to the power 4 t to the power 4 by h cube c cube times x cube by e to the power minus x e to the power x minus 1 dx. So at a constant temperature, if you look at it, this you need to know value for this integral, and in order to know that, just remember this, that 0 to infinity x cube e to the power x minus 1 is equal to pi by 4 pi to the power 4 by 15. So this is what we need to substitute here, and we will get the expression for E lambda as 8 pi to the power 5 kb to the power 4 t to the power 4 by 15 h cube c cube, and the whole of this is constant. The whole of this is constant, which is given by sigma to the power 4, and I wrote R, the radiative power, is c by 4 E lambda, and this is some constant. This is c by 4 sigma times t to the power 4, and this is sigma star t to the power 4. This is actually the Stephen Boltzmann constant. This is the Stephen Boltzmann constant.
So, by Planck's derivation, we can obtain these two characteristics, which shows that the expression used by Planck, or the theory which Planck, which his brilliant mind brought into picture, is right, and this explains many things. And for this part, the black body is finished actually, and we will look into some other experimental observations which brings the quantum theory or the quantum picture into account. And for this, thank you so much for watching this, and I hope this helps you further. Thank you.